Exam 3 is coming up, and since we're not covering Chapter 16 on this exam, we have a little bit more time than we would have, so let's do a review of everything we've covered so far. So generally, what we've been covering between the two exams is general kinetics, not enzyme kinetics, but the general kinetics that apply to every chemical reaction, whether it be an enzyme or something simpler like the water-forming reaction. To begin with, let's just get the preliminaries out of the way. The exam is this coming Monday, less than a week away now, from 8 to 10 p.m. It'll be done by Respondus. You upload your exam at the end as if it were a homework. And an 8.5 by 11 cheat sheet is allowed. All those things are the same as they have been for both previous exams. Again, yes, only Chapter 15, not Chapter 16, no matter what the syllabus may say at the moment. And I have actually mostly written the exam, and there will be 5 questions. All right, so starting with the basics of kinetics, the rate of reaction itself. The definition of the rate of reaction is the rate of change of something that correlates or relates to concentration. Oftentimes it's concentration itself, sometimes it's pressure, sometimes it's other quantities that relate to concentration. That's straightforward enough. If the reaction is elementary, then the rates of reaction for the various different possible species, both reactants and products, are related to each other. That's true if it's an elementary reaction or if it's a steady state reaction. And the relationship is this, that if you divide each derivative, time derivative, rate of reaction by its stoichiometric coefficient and multiply by a minus sign for the reactants but not for the products, then all of those rates are equal to each other. So for this fairly broad special case, it doesn't matter which species you use to monitor the rate of reaction. They're all very closely related to each other. Again, as we've seen since the last time we talked about this in the original lectures, the reason why this relationship applies for elementary reactions is that there are no intermediates. So every time an A is lost, every time A molecules is lost, B molecules is also lost, and C molecules and D molecules are created. And so obviously, given that, the rates have to be related to each other. If you're at steady state, then all the intermediates that may exist in the actual mechanism don't change their rates. So we're at steady state after all. And so in that case also, all these same stoichiometric arguments hold in that case. However, if the reaction is not at steady state and is not elementary, then these relationships don't hold anymore. All right, then there are rate laws that give how the rate of reaction depends on the concentrations of reactants and products. Usually it's just reactants that appear in a rate law, though because you can derive a rate law from a mechanism and because the mechanism can turn some products also into reactants in some steps of the mechanism, it is possible in principle for products to also appear in rate laws. That's unusual, but it does happen. The most common, we've seen in the we've seen if you look ahead a little bit in the Michaelis-Menten mechanism that rate laws don't have to be power laws. Some of them aren't. The Michaelis-Menten mechanism isn't. But the most common form is a rate law, is a power law, in which case all of the product or the concentrations that appear are raised to powers, and in elementary reactions, those powers are related to the molecularity of the reaction. We'll talk about that down below. But for overall reactions, because the rate laws then emerge from complicated calculations within the mechanism, they don't have to be related to molecularity. They don't even have to be integers. They don't even have to be positive. The powers can be, in principle, anything. It's unusual to get these kinds of weird rate laws. Actually, a power of a half is pretty common. But a negative rate order or power is uncommon. Things like a third and some random fraction are even more uncommon. So usually it's integers, positive integers, or possibly a half occurs fairly often. If the reaction is elementary, then there are only, for our purposes, there are only 3 rate laws. It's only first and second order reactions that are appreciably that are elementary. Third order elementary reactions exist, but they're extremely rare, so we'll just ignore them for our purposes. And in that case, these are all the possible rate laws that come from elementary reactions. There's the first order case, there's only one of those, and then there are 2 second order cases depending on whether the collision is between 2 A molecules or between 2 molecules of different types. A reminder that the rate constant for first order reactions has units of seconds to the -1, but for second order reactions it has units of molar to the -1 seconds to the -1, and in general the units on the rate constants depends on the overall order of the rate law. We saw that it is possible to find the rate law for a chemical reaction in a fairly straightforward and simple way by measuring the rate of reaction very early in the course of the reaction before any of the reactants, any of the products has a chance to be depleted and any of the products has a chance to build up. Here's an example of this for a reaction that has 3 reactants and any number of products. The products don't really come in here. I just put P to indicate any number of products here. So here's our 3 reactants, A, B, and C are reactant concentrations. And since there are 3 of them, you need at least 4 rows of data in order to have enough data to determine the rate law. And then the 4th column here is the rate itself. Under these conditions for concentrations, so notice that in every case, the first row has all the same concentrations. The second row, though, has one of the concentrations doubled. In the third row, that concentration has gone back to its original value, but a different concentration is doubled. And in the 4th row, the third concentration is doubled. So basically, we're just changing one concentration at a time, keeping all the others constant. That's the strategy behind doing these kinds of, or collecting these kinds of data. And now the way you use that data is with these formulas. We derived those earlier. I won't rederive them now. We're looking for powers or orders for each of the 3 reactants, and also we're looking for the value of the rate constant. For A, the power will be the rate for row 1 plus the rate for which that concentration changes. Take the log of the ratio of those 2 rates and divide it by the log of the ratio of the 2 concentrations that are different. And that should give you the order. And in this case, it turns out to be 0.496, which, with experimental error, that's probably an order of a half. In the case for B, it's again the 2 rates that correspond to the 2 rows where B changes. And so it's R3 over R1 divided by log of B3 over B1. That's log of 1.59 over log of 2, and that's 0.67, which is about 2/3. And likewise for C, it's row 4 over row 1 for both rate and concentration, and that gives a power or C exponent or order of about 3/2. So that means that our overall rate law is K times A to the 1/2, B to the 2/3, C to the 3/2. I don't think there's a single reaction on Earth that actually has such odd powers in every single case. I don't know what kind of mechanism would give rise to such a rate law, but all right, in principle, it could be something like that. And I chose these weird, odd powers so that just to illustrate the range of possibilities. All right, once we know this, we can choose the data from any one of the lines in the table. So we could use line number 2. I actually used the data from line number 1 in order to get the rate constant, because we used the R value from row number 1, and then the A, B, and C values from row number 1. Plugging those in gives 464. What units should it be? Well, you can see right away, right? Molar per second on top, and then molar to various powers on the bottom. And if you just work out what that is, it's molar to the -5/3 seconds to the -1. So as I said earlier, the rate constants have weird units sometimes. This is an example of that. Of course, this is a very fake, artificial, on-paper kind of example. You're not likely to see units like this or orders like this in real life, but they're good for illustrating the principles. All right, then we talked about integrated rate laws, 2 types, first order and second order. For a first order situation, the elementary reaction that corresponds to this case is A goes to products of any whatever kind. Differential equation is dA dt is minus Ka. The solution to that, full solution to that, is A equals A0 e to the minus Kt, so an exponential decay. There is a linear plot that you can use to prove that it's first order. Plot the logarithm of A versus time, and you can see from this form of the solution that that should give us a straight line. And the slope of that straight line is equal to minus the rate constant itself. First order reactions also have this important special property that their half-lives are all equal. If you wait until the initial concentration drops by a factor of 2, and then wait till that concentration drops by another factor of 2, you'll wait the same amount of time both cases, and that will be true for every other factor of 2 after that. And that's illustrated, or that fact is encapsulated in the fact that the half-life for a first-order reaction doesn't depend on the initial concentration. It's just 0.69, well, it's log 2 divided by the rate constant itself. If you can find the half-life, therefore, you can easily find the rate constant itself. And so first-order reactions lend themselves to very easy analysis. I didn't write this before when we were going through the notes, but it's also possible to write the exponential decay that I've written up here with an exponent with a base of log e as the exponent. It's also possible to write it with a base of 2. And in that case, the concentration versus time is the initial concentration times 2 to the t over the half-life as a well, that's the power, t over t to the 1/2, which shows right away that when t is equal to 1 half-life, you'll get 2 to the -1, so you're down by a factor of 1/2. When you've got 2 half-lives, it's 2 to the -1/4, and so on. So this form of the relationship shows clearly this property that the half-life is constant. The fact that the half-life is constant also means that you can do a very informal kind of experiment. And this is very useful in field situations where you don't have a lot of laboratory equipment. Let's suppose you're at a pond and there's some pollutant in the pond, and you're measuring the concentration as the pond slowly clears itself of the pollutant. Is it a first-order reaction? Well, you measure how long it takes for the pollutant to drop its concentration by a factor of 1/2, and you measure that time. Then you do that again when the concentration drops by another factor of 2 down to 1/4 of its original value. If those 2 times are the same, then you have a first-order reaction and you can get the rate constant right away. If they're not the same, then you have something more complicated, either second order or something that doesn't even fit in the first order or second order list of possibilities. All right, for a second order reaction, the elementary reaction is 2A goes to products. The differential equation is dA dt equals minus Ka squared now. Solving gives you that the concentration is 1 over the initial concentration plus Kt. This version of the rate law, of the integrated rate law, shows that if you plot 1 over A versus T, then you'll get a straight line if it's second order, and the slope in that case is equal to K itself. So these two plots, the 1 over A versus time, or up here, the log A versus time, are diagnostic or characteristic for first and second order reactions, which are by far the most common case, and so these plots are very widely used, very useful. All right, then that is all of the basics. Then we moved on to talking about mechanisms and elementary reactions. An elementary reaction is a reaction that doesn't have any intermediates. That means it has to be simple. It has to be a one-step kind of thing. The order of reaction is equal to the molecularity. The order is 1 if there's only one reactant. It's 2 if there's 2 reactants. All elementary reactions are by definition irreversible. If the reaction in question is reversible, then that's 2 elementary reactions, one for the forward process and one for the backwards process. Elementary reactions are used to build mechanisms, and therefore all complex reactions are built out of collections of elementary reactions. As I said earlier, for a first-order elementary reaction, it's something where the reactant itself just changes on its own. In this case, a conformational change. Here, in this case, a spontaneous bond-breaking event, and so on, those kinds of processes. The second-order cases are pretty much all collisions of some kind. So an H2 molecule colliding with a Cl2 molecule here, creating an HCl molecule and some loose atoms. That's an example of a second-order collision reaction. A mechanism, of course, means that if you have some complex overall reaction like this one, then the mechanism is composed of all the elementary steps that actually cause the reaction to take place. So in this case, a possible mechanism, I'm not sure this is the correct mechanism, though I think it's something like this, is that the I2 bond is actually fairly weak, and so the I2 splits spontaneously into 2 iodine atoms. Then one of the iodine, or it can go backwards. 2 iodine atoms can come together to form an I2 molecule again, so both forward and reverse reaction. Then the loose iodine atom could collide with an H2 molecule, take one of the H atoms away, and leave behind a loose H atom, which can then collide with an I2 molecule, form another HI, and leave behind another loose iodine atom. That's a plausible mechanism. Much more can be said about that mechanism. In fact, it's an example of a chain reaction mechanism, which are the explosive kind, along with a whole lot of other properties they have, but we only have so much time this semester, so no more comments on that. We will use this mechanism, as we've used in the other case, to illustrate the process of writing the rate equations from a mechanism. So there's one rate equation for every species in the mechanism. In this case, for example, there's one for I2, there's one for I, there's one for H2, there's one for H, and there's one for HI. Just to take one of those, let's take the one for the intermediate, the I atom concentration. The rate of change for that would be a term from, so I, notice I've got them circled in green here. All the I atoms appear in every single reaction in the mechanism. That's unusual. Usually any one given species only appears in a subset of the mechanism, of the reaction, of the elementary reactions. But in this case, it appears in every single one. So for the first one, I is created. The rate law for that is 2 times K1, that's K1 here, times the I2 concentration. It's always the products that appear in the rate laws for elementary reactions. The 2 here is probably the hardest part to explain and to get straight. So I've put a few notes down here to make that easier. There's a 2 here because, first of all, we're looking for the rate for I2, and the 2 appears on I2 itself in reaction number 1. And I show that down here. Reaction number 1 has the 2 on I itself. We're writing the rate equation for I, and it's I that has the 2. And therefore the 2 appears in front. If we were writing the rate equation for I2, the 2 wouldn't be there. If we were writing di2 dt. If we were writing this rate equation, even though the 2 is over here, it's not on I2 itself, and so it wouldn't appear in the term from reaction number 1. All right, so we can go on. So here's the term from reaction number 2, which is just the reverse reaction. That's a second order case, right? Here's the term from reaction 3, which is again a second order reaction. Here's the term from reaction 4, which is a second order reaction producing an I on the other side. Notice that the plus signs apply whenever I is created in reactions 1 and 4, and minus signs apply whenever I is consumed, as it is in reactions 2 and reactions 3. All right, so that's what a mechanism is. That's how you write mechanisms. Let's stop here for now, and I'll pick up again later with another lecture.